Hello and welcome to the Chandra Academy. Today we're going to solve the problem of the 2021 exam. So we are given a function f with some expression. We will first find the domain of f, then calculate the limit in plus and minus the infinity. Then we will prove that the curve of this function has an oblique asymptote in plus the infinity. And then we will derivate the function and prove that the derivative exists. And in conclusion, we will prove that the curve to the function has a tangent line in x is equal to 0, parallel to the oblique asymptote. Okay, so first, let's write down the function. So f is a function that given x gives x minus 2 plus 2x plus 1 over exponential of x. So we will try to find the domain. So the domain, which is the largest intervals, reunions of R, where f exists. So basically, the largest interval reunion where we don't have any problem with the function. So where could our problem come from? Not from this polynomial part of the function, but with this quotient if we had the denominator equal to 0 for 1x. Do we have our denominator equal to 0? No, because exponential of x is always strictly superior to 0. So no division by 0. Okay, so the domain is R, because let's explain, because x minus 2 polynomial defined for R 2 times x plus 1 same thing, exponential of x defined for R, and then quotient, so the division between 2x plus 1 over exponential of x defined for all x in R, because exponential of x is different from 0 for all x in R. So D, our domain, is equal to R. We answered the first part of the question. Now we will try so let's remember f of x is equal to x minus 2 plus 2x plus 1 over exponential of x. Let's find the limit of x, f of x, in plus the infinity. Okay, so this will tend to plus the infinity, and this is equal to 2x over exponential of x plus 2 over exponential of x. So the exponential of x here will tend to plus the infinity, so this will tend to 0, either for one infinity or the other. Okay, and for this part we've got this indication. You should know it by heart. That gives us that the limit of x over exponential of x when x tends to plus the infinity is equal to 0. So this will tend to 0 when x tends to plus the infinity. So we've got, let's write it down clearly, x plus 2 that tends to plus the infinity when x tends to plus the infinity. We've got 2x over exponential of x that tends to 0 when x tends to plus the infinity. And we've got 2 over exponential of x that tends to 0 when x tends to plus the infinity. And so, by addition, we've got f of x that tends to plus the infinity when x tends to plus the infinity. So we've got a plus 0, but I won't write it down. So first part of the question. So now, let's remember f of x rapidly. 2x plus 1 over exponential of x. So what will happen when x tends to minus the infinity? Okay, so we will have x minus 2 that tends to minus the infinity when x tends to minus the infinity, clearly. And then we will have this part that will tend, so minus the infinity, 1 doesn't matter, 2 positive, so it's still minus the infinity, so it will tend to minus the infinity, and this will tend to not minus the infinity, but 0, because exponential of x tends to 0 in minus the infinity. Okay, so be careful. So minus the infinity over 0 plus, so that's still positive. This quotient here will tend to minus the infinity. So 2x plus 1 tends to minus the infinity when x tends to minus the infinity. Exponential of x will tend to 0 but plus, so a positive 0. This is important to get the sign of the quotient when x tends to minus the infinity. This implies that 2x plus 1 over exponential of x will tend to minus the infinity as well when x tends to minus the infinity. And in conclusion, by addition, we will have f of x that will tend to minus the infinity when x tends to minus the infinity. Okay. So, now that we have the definition of the function, the domain of definition of the function, and the two limits, let's start with the second question, proving that line D, which has the equation following, is an oblique asymptote of C in plus the infinity, and specify the location between the two. So, how do we answer this question? You have f of x, let's remember, is equal to x minus 2 plus 2x plus 1 over exponential of x. How we should answer this question? So y is equal to x minus 2. So y is the equation of an oblique asymptote to C of x if and only if we've got f of x minus y of x, so in the plus the infinity, tend to 0 when x tends to plus the infinity. What does it mean? It means that if we've got our function, our curve c of the function, and our asymptote here, so let's call it d, we will have this thing that goes to 0 when x tends to plus the infinite. So we've got something which has the comportment of a regular line in plus the infinity. This is the thing to understand. So let's try to see if it works. So f of x minus y of x is equal to x minus 2 plus 2x plus 1 over exponential of x minus x minus 2. Okay, so this being the equation of f of x, and this being the equation of y of x. So this thing, let's call it delta, because this is a difference, is equal to 2 times x plus 1 over exponential of x. And we can see that firstly we wanted to know the location of the graph with respect to the line. So we're doing something like f minus g minus y. So we've got this thing that is superior strictly to 0 when x strictly superior to 0. So the case we're in, because we want to go to plus the infinity. So we've got c that is above d, c being the curve of the function, d the curve of the line, and then the potential line, and then as we proved before, this will tend to 0 when x tends to plus the infinity. So so proof in the first question. Okay, so we just proved that d has an oblique asymptote of equation x minus 2 in plus infinite, and that c is above d. So d is an oblique asymptote to c in plus infinite, and c is above, so on top of, above d. And we answered the question. Okay, now let's next question. We want to see if f has a derivative, and prove that this said derivative has some expression. And we are given a result, and with this result we will try to study the variation of x. So let's remember little c, f of x is equal to x minus 2 plus 2x plus 1 over exponential of x. As said, the domain of definition of x is equal. So let's see, we will not have any problem with the derivatives because exponential is an easy function, and this is your only part of the function. So with the question that could go wrong. So everything has a derivative for all r, for all x, a real number. So the domain of x is equal to the domain of f prime is equal to r. So let's derive the function for all x in R. F prime of x exists and is equal to, so for this part, easy, we've got 1 plus, so we've got something like u over v, and when we derive that, we've got u prime v plus u v prime over exponential over, over v squared, and that's a minus, so minus here. So let's do this with this thing being u and this thing being v. Okay, so everything on top of v squared, so exponential of 2x, and we've got u prime, so 2, times exponential of x, so v, minus exponential of x prime, so exponential of x, times 2x plus 1. Okay, so let's simplify this expression. So we've got 2 exponential of x over exponential of x squared, factor of 1 here, and on the other part, minus x plus 1. Okay, so you've got 1 plus, let's simplify this one with this one, 2x over exponential of x is equal to exponential of x plus 2x over exponential of x. F prime of x is equal to this whole thing. Did we make any mistakes? Let's see, because we've got the result here. We did not make any mistakes. Yes, we did some mistakes. There is a minus here, minus, and we've got our final result, because I made a little mistake with this minus not being here. So that's the type of thing you need to verify during the exam. So now we know that we've got this being true. Use this result to study the variations of x. So if exponential of x minus 2x superior strictly to 0 for all x, and exponential of x being positive for all x as well, that implies that f prime of x is strictly superior to 0 for all x. So that f is going up in R. So for all x's in R, f prime of x is superior to 0. So x is going up. Okay, let's say that's not the right term, but we will sum up with a variation table. So value of x, sine of f prime of x, variation of x. So we've got this little table. So x goes from minus the infinite to plus the infinite. We know that the sign of f of x is positive for all x. We also know that the function, so variation of f, sorry, so the function goes from in minus the infinity minus the infinity, in plus the infinity plus the infinity, and that is, it's just going up. So we've got something like that, and this sum up all we said. Okay, so done for this question. Now prove that C has a tangent line delta at x is equal to 0 and parallel to d. Okay, so what does it mean? So little d, so f has a tangent line if and only if f prime of x, so line in x, f prime of x exists. Okay, so we know that f prime of 0 exists because 0 is in the domain of f prime, and so the tangent line has a direction coefficient of f prime of 0 is equal to exponential of 0 minus 2 times 0 over exponential of 0 is equal to 1. So we've got something like, if the function is like this in 0, hopla, so 0, we've got something like that, so a tangent line with a rate of 1. With a rate of 1. So now we just proved that C has a tangent line delta at x is equal to 0 and parallel to line D. So why parallel to line D? Because let's remember D, which has the equation y is equal to x minus 2, as also the direction coefficient of 1 for all x's. So for 0, for instance, but if it's right for all x's, we can say that the tangent line in 0 for the curve of x is parallel, because we've got this equality and this equality, so we can say that those two are parallel. Then now, what do we want to prove? That's the whole thing. So we just need to know through which point does f prime of 0 pass through. Okay, so f prime, so we've got delta that goes through because it's tangent. F of 0 is equal to 0 minus 2 plus 2 times 0 plus 1 over exponential of 0. So it's equal to 0. So let's sketch it. We've got our y axis, our x axis, and then we're going first to sketch our tangent delta in 0. Okay, delta, which has a rate of 1. Then we're going to sketch the oblique asymptote, which is called D, that has an equation of y is equal to x minus 2. So in 0 it's equal to minus 2. And it's parallel to delta, so something like that. Okay, And then we're going to sketch our function that goes from minus the infinity, that is tangent to delta in 0, and then that goes rapidly because of the division by exponential of x to the asymptote. Okay, so we've got something minus infinity, we've got our tangent here, and then we've got something that goes like this, and it's called C. So we are done with our problem. Hope you enjoyed the video. Bye.